Okay, this is a screencast to accompany the following PowerPoint presentation. I always show this PowerPoint in class. I'm going to have to split this screencast, however, up into two parts. Okay, now with respect to optical atmospheric phenomena, pretty much everything that you see in the sky only has one source of light, and that's the sun. Of course, some exceptions would be lightning, say in auroras, but those are caused by entirely different physical phenomena. Hey, here's a nice picture of the solar spectrum, the entire Roy G. Biv portion of the spectrum. The sun is a hot object, so it basically gives off visible light in all colors. What you're seeing here is the dispersion of sunlight through some piece of beveled glass that I have sitting on my windowsill. On afternoons at particular times of the year, the sunlight will strike that beveled glass at just the right angle. The beveled glass acts like a prism, and it disperses the sunlight into the solar spectrum. You're seeing the solar spectrum here cast onto the side of my refrigerator. Okay, briefly, let me describe why the sky is blue in normal sunlight. Okay, the sky is blue because light of blue wavelengths scatters more efficiently off of air molecules than all of the other colors. This is what is referred to as Rayleigh scattering. As you can see here in the slide, the scattering of blue light, which has a wavelength of about 400 nanometers, is roughly 10 times as great as that of red light, which has a wavelength of 700 nanometers. This is why the sky appears blue as opposed to red. However, of course, you can see red light associated with the sunset. The reason for that is as follows. Let's say that the sun is really low to the horizon like so, or is just setting below the horizon like so. And then you have sunlight coming from the sun. It's refracting through the atmosphere, so it bends a little bit and then strikes the observer over here. When the sunlight is passing through this long tunnel of atmosphere right here, basically by the time that it reaches the observer's eye, all of the blue light has been scattered out. So then therefore the red light of the sun remains, and that then is why the setting sun appears red. Okay, here's a nice picture of what is called the green flash. In order to see the green flash, which lasts for only a moment, right at the moment of sunset itself, you basically have to have absolutely pristine conditions. You have to have a very still atmosphere that is nice and crisp and there's no dirt associated with it. And you also have to have a completely flat, featureless horizon. The best time to see this out over the ocean, for example, here, say in Santa Monica Bay, is usually in the late autumn or early winter months when the atmosphere is basically still, a nice clear day, and it's basically very clean. And then just for a moment here, right at the moment of sunset, you could see a little bit of a green light like so. That's called the green flash. I took this photograph, for example, in Hermosa Beach in November of a couple of years ago. And here's what you're seeing. Okay, so way over here is the setting sun like so, and then you have sunlight dispersing into its component colors as it refracts through the atmosphere. And then the observer is actually standing right over here in this graphic. You're never going to see what is called a blue flash because by the time that the light reaches this location over here, it basically has bent too much or it's already scattered out of the atmosphere. The red light itself is above you. In other words, that portion of the sun has already set. But if the angle is just right and the conditions are just right, the green light here will in fact refract into your eye like so, so that you can see for just a moment a green flash. Okay, this right here is what's called a sun pillar. You're basically looking at the refraction of sunlight here through ice crystals in the upper Earth's atmosphere. So here in California, you're usually only going to see something like this, say in late autumn or during the winter. Okay, here's a beautiful photograph of two rainbows, the primary as it's called and the secondary. Okay, notice that the secondary is a lot dimmer, of course, than that of the primary, and the order of colors in the secondary is reversed as opposed to that of the primary. Okay, the physics of rainbows is kind of complicated, but you're basically seeing here the combination of several different effects. First of all, dispersion, and then secondly, total internal reflection. Here's the basic idea. Okay, so here's the observer like so, and then the sun is off in this direction like this. And then we have the sun's rays coming in parallel to each other like so. This is the white light associated with the sun itself. And then the sunlight then enters these water droplets, which are spherical like so. The primary rainbow is only going to be seen at roughly a 42-degree angle as measured from what is called the anti-solar point. And then when you look in that direction, the angles are just right for the following to happen. You have the white light from the sun beginning to disperse into its component colors as it enters this water droplet. And then the light right here at the back end, or the back side of the water droplet, undergoes total internal reflection, and it then refracts out of the water droplet back into the air like so. Now take a look carefully at the order of colors here. Here is, by the way, a larger graphic that shows it. And notice that the angles here are slightly different from each other. Also notice that the order of the colors here, like so, for the primary, is reversed with respect to what you see. And the reason for it is because you're basically looking at right here a column of water droplets. So you're looking at slightly different angles. When you look, say, at the 40-degree angle, then you're seeing the violet light. And then when you look at the 42-degree angle, then you're seeing the red light, like so. Okay, now here's what's happening in the secondary. So you've got white light coming in from the sun like so. It then starts to disperse into this water droplet right here. And then you have 1, 2 total internal reflections that occur, and then the light eventually refracts out of the water droplet like so. Notice that the order of colors here is reversed in the secondary as opposed to that of the primary when the light emerges from the water droplet. You can see that pretty nicely here in the photograph. And then in addition to that, the light itself is basically inside this water droplet longer than it is for the primary because there's 1, 2 total internal reflections that occur. So then therefore more of the light is absorbed within the water droplet itself, and then therefore the secondary rainbow here appears dimmer. Okay, here's what's called a sun halo. I'm sure you've seen this before. Basically, this is the refraction and the dispersion of sunlight through ice crystals in the upper Earth's atmosphere. So you're only going to see something like this usually in, say, the late autumn or during the winter months. The ice crystals themselves, however, have to have a hexagonal shape, as is shown here in this simple graphic. And then you have sunlight coming in, it then splits up into its colors as it disperses and refracts. And then there's an angle here of 22 degrees with respect to the original direction of the sunlight itself and the direction here of the halo that you see. There is a 22-degree angle here between the sun and the halo itself for that reason. Sometimes associated with sun halos, you have a whole host of other phenomena here that you may have seen before if the conditions are just right. Have you ever seen a splash of color, say off to the side, for example, like so, of the setting sun, like say during the late autumn or early winter months? Well, if you have, you're seeing what is referred to as a sundog. It's just more detail that comes out if the conditions are just right in a sun halo. Here's a nice graphic that shows all the different things that can be seen under the right conditions. What I've posted for you, by the way, in today's folder is an awesome film. It's only about 30 seconds long of a sun halo and all these other details of sundogs and so on and so forth that were seen at this particular moment. It was taken in the wintertime at a ski resort in Sweden. It's only about a 30-second long clip. I posted a clip for you in today's folder. I encourage you to take a look at it. Sundogs themselves, by the way, are sometimes referred to as Parhelia. Okay, here's a moon halo. It's basically the exact same thing, except in this case, you're just looking at sunlight that's reflecting off the moon, and it then disperses in the manner I've already described. Okay, let me end this right here as part 1 of this particular screencast. I'll post a part 2 in just a few moments.